Hello, it's December 30th, 2021. I just want to make a short video. I'm sitting at home watching these videos on YouTube about physics, and I keep hearing this one thought experiment. I guess it's by Einstein. All the physicists use it. I understand what they're trying to say, but to me, it seems like it's fundamentally wrong. Here, I'll start it and then I'll show you what I mean.
You probably have a rough idea of what the laws of physics means. Motion, matter, energy, all the equations that govern the universe. So what does it mean to say the laws of physics are the same in all inertial frames of reference? Well, I could tell you, but I'd rather show you. Imagine you're standing on the ground throwing a ball in the air. It's only moving in the vertical direction, straight up and down. You then see me move past you with some constant velocity, also throwing a ball in the air. You see my ball trace out an arc or upside down parabola if you're feeling fancy. You conclude that because my ball is moving both vertically and horizontally, you must be standing still and I must be moving to the left. But let's look at things from my reference frame. Here I am, happily throwing a ball on the back of a vehicle, watching it go up and down in the vertical direction. I see you, and this time it's your ball that's tracing out a parabola. I therefore conclude that because your ball is moving both vertically and horizontally, I'm the one who's standing still and it's you and the ground that are moving to my left. The laws of physics, in this case motion, work the exact same way for both of us. There is no experiment we can perform to tell us who is standing still and who is moving.
All right, well, so they don't know. Well, I got a few ideas. Let me go back here. See, when she's on the ground, the ball, it goes straight up, pretty much comes straight down. The Earth is rotating at 1,000 miles an hour, but you don't really notice it here. But it's different when she's on the truck.
Must be moving to the left. But let's look at things from my reference frame. Here I am.
Okay, when she throws the ball up, did you see it started to go to the left? That's because the truck is moving to the right. And when she throws the ball up, it has forward inertia because she was just holding on to it. But then once she releases it, Earth's gravity starts diminishing the forward inertia. So it starts to slow down, starts going, then Earth's gravity starts to take it. So it's going to land over here somewhere. And you can see her move her hands over.
Happily
Okay, so you move her hands over a little bit.
throwing a ball on the back of
That time too. See, it happened again that time. Let's see if she does
a
it again.
vehicle, watching it
Yeah. See, it happened one more time. Let me show you that.
ball on the back of a vehicle.
Okay, it goes up right there,
Watch
and it went up right here, and it's coming down here. Okay, that doesn't happen when she's sitting on the ground. So that's a difference right there. Plus, okay, her arm when she's sitting on the ground with the ball, she's got her arms put a force into the ball. Let's say she throws it up at 5 miles an hour. The Earth's rotating at 1,000 miles an hour. So that's let's just say it's 105. Let's say it's 1,005 miles per hour when she's sitting on the ground. When she's on the truck, her arms throw the ball up 5 miles. Earth's at 1,000, but the truck's at like 5 miles an hour. So let's say it has it has more energy. Let's just say it has 1,000. It's going 1,010 miles an hour. The energy when she's sitting down, the ball's just going to go straight up and down like this. It has this is Earth turning, rotating, but yet we don't notice it that much in this instance. But over here, you got the truck. You got another force affecting the ball when she's throwing it up and down. So here, when she's on the ground, it's going to look like this. to her, and then when she's on the truck, it's going to look like this to her. So that's the difference. And when you're uh, when you're on the truck and she's the arc of the ball on the ground is going to look different. It's going to look like this. When she's on the truck, the arc is going to, when you're on the ground looking at her on the truck, the arc might look more like this. So that, that's a few things that are different. Um, the ball, this ball will have just overall less energy. This is going to have more energy because it's got that extra energy from the truck going at 5 miles an hour. So these differences they might be important, and it seems like these physicists they never mention it, and then they just keep building more ideas on top of this idea that you can't tell the difference between uh, this observer and the observer on the ground, but you can tell the difference. You can calculate it, and it might make a difference. So I don't think they should just skim over it quickly. She's gonna so I guess I'll just end it there. She talks about this clock. All the physicists
From
do.
your frame of reference, you see it bounce like this,
See this
tracing
clock.
out a diagonal path as it bounces between the mirrors. From your frame of reference, the light beam traveled a longer distance.
See the all the physicists. Some call this a photon clock. They shoot a photon and it bounces back and forth. But I don't even think it would stay in between these. It might stay in between the mirrors if the clock is perfectly still. But if the clock's moving on a truck, I think this photon will just keep bouncing back, but stay vertical. And as the truck moves forward, it'll just keep moving over this way. It'll just escape out the side, because if you notice on the truck, see when she throws it up,
Happily throwing a ball on the back.
She has to reach over to a little bit farther this side, but then she brings the ball back and throws it up again. What if she moved her body over here and then threw it up? The ball would go over here, and then she'd have to take a step over this way, throw it up, take another step, and after a while she would fall off the tailgate.